Okay, for part A, they want a free body diagram for a block M, for all the forces on block M, little m. So draw this block little m. And you have to draw all my forces. Well, I know that there's going to be a tension force here, right? But that's not given in the diagram. They don't label it. So what is that motivated by? Well, I see this one string right here, right? This string has the force of F, and this is one string, so it wraps around. So that means I know there's two F's pulling it upwards, right? So I know that this force here is just going to be 2F, right? So I'm going to need an arrow up here. That's 2F. And then I know there's friction, right? Friction that acts against my line of motion. So I know there's going to be an FK like this. And the FK is a little smaller because I know that friction and then the force of FGX that's trying to pull it down, the gravity from the slope or whatever, right? Gravity's acceleration in the x-plane. It's going to try to pull that down, right? So I'm going to draw this FG bigger than what it should be because I know that it has components because my plane is like this. X and Y, right? So because it has planes like that, I know that FGY is going to be this Fn force right here, this normal force, this reaction force, right? So then some of that's going to be Fn, and then the rest is going to go towards FGX, and FGX combined with FK would be about like 2F's length because it's constant velocity, so that's why I scaled it how I scaled it, because some of FG goes into the normal force, but some of FG also goes into FGX, which FGX and FK combined should be 2F because it's moving at constant velocity, so that's why I scaled it how I scaled it. Part B. For part B, they want an expression for the magnitude of the pulling force in terms of the variables given and any fundamental constants, right? Well, since it's constant acceleration, I know the forces acting in the x direction are going to equal 0, right? I don't need to worry about the y direction because FGY cancels out Fn, right? So I'm just focusing on this horizontal motion on the x-plane, like that. Okay? So what are some of the forces? Well, it's going to be 2F minus, because it's acting against FK, and then minus FGX. It's going to be equal to 0, right? But it wants it in terms of the variables, right, to find what F is. So first off, let's get F on one side because I'm going to be isolating for F later on. And I got it by that side by adding FK to both sides and adding FGX to both sides to cancel it out on the left side and put them on the right side. Let me make this neater. Okay. And with that, now I just need to change it into what the graph gives you, right? So first off, let's look at FG. I know FG is going to be pointing downwards like this, right? But because my axis is like this, where this is X and this is my Y, it's going to have components. I know there's going to be an FGY like this, right? There's going to be this normal force, which is equal to that FGY's length. It's the same magnitude. And there's going to be FGX. Okay? With that, I can find what these are in terms of the diagram given. So first off, let's look at FGX, because I found FG. So let's get FGX out the way. So what is FGX? Well, I know the angle of the ramp is the same as the angle created between FGY and FG, right? So I'm just going to call that theta. So I know FGX, since it's opposite to the angle, right? It's going to be FG sine theta. But what is FG equal to? mg, right? So I'm going to rewrite that. FGX is equal to mg theta, sine theta, mg sine theta. I'm going to rewrite it like that because they give you little m. So I want to respect the diagram. So mg sine theta is FGX. So I'm just going to put mg sine theta down there. Like so. And then I need FK. Well, what is FK? I know FK is equal to mu k times Fm, right? Well, they give me the variable mu k, so all I need is Fn. But I don't have Fn, it's not given in the diagram. But I know that Fn is going to be equal to Fg's y component. And FGY, since FGY is adjacent to the angle, it's going to be cosine, is Fg cosine theta. Again, Fg is mg, so I'm just going to rewrite that as mg cosine theta. And that's what FGY is going to equal to. And with that, I can say Fn is also equal magnitude-wise to mg cosine theta. Okay? So, because of that, I can plug in. Here, I'm just going to put fk on the other side. Well, I'm just going to put fk in front. I'm going to move it in front because I wrote fgx first already. Okay? So then fk is simply going to be mu k times what fn is. And what did I define fn to be? Mg cosine theta. Okay? And that's equal to 2f. Now I'm going to divide both sides by 2. And that gets me the expression for f. Magnitude is over 2. So the magnitude of the pull force is at this expression right here. And I can just put magnitude, and I don't have to like absolute value the other side because this is all looking at magnitude already. I incorporate the negatives here and this magnitude. This is the magnitude, so they're all in magnitude. I plug in the magnitude of the values. So now magnitude of f is equal to that. Let's go on to C. Now for C, they say if the angle of the ramp is decreased, what happens to the magnitude of the applied force, right? Well, this is my expression for the magnitude of the applied force. Bring that down, because I'm going to be looking at that. Now, if the angle were to decrease, so that's saying these thetas right here, I'm just going to show that they're decreasing. Right? Then what happens to this f right here? Question mark. Well, we see that sine, as you decrease the angle, because you know sine of 90 degrees is 1, and sine of 0 degrees is 0. So as I decrease the angle, this sine expression right here is going to want to decrease. But as I also decrease the angle, this cosine expression, I know that cosine of 90 degrees is 0, but cosine of 0 degrees is 1. So I know that as I decrease the angle, cosine is going to be increasing, this expression right here. So that leaves me with the problem. This one's decreasing, but this one's increasing. How do I know which one has more impact, right? And the answer lies with mu k. Since this problem gives me no further information, mu k, according to physics and Google, is typically less than 1. I'm going to write typically. Typically. Less than 1, right? Since mu k is typically less than 1, that's what I'm going to refer to. Okay? So since I'm assuming mu k is less than 1, assume, comma, mu k is less than 1, typically, yes. That means I'm going to be multiplying this increase by a fraction, while this one is just decreasing, there's no fraction to it, right? If I'm saying mu k is less than 1, I'm getting whatever this is, and I'm dividing it by some said number, right? And because I'm dividing it by a number, and they're changing at similar rates, equal rates actually, where sine and cosine have like an inverse relationship where sine is decreasing at the same rate as cosine is increasing as the angle shifts, right? That means I know this mu k is simply going to make this part of the expression increase a little bit less because this mu k is going to be a fraction, so I'm going to divide this number by some number, right? So that's going to make it smaller. So it's going to be increasing a little smaller than the rate it's decreasing, right? So if it's decreasing more, then ultimately decreasing takes priority, and I can say that the applied force I need will decrease. So D, with all this information, right, calculate the applied force needed to accelerate the block up the slope. Now with D, I can't say this anymore, because this is where I assumed, hey Mr. Wong, I know the symbol is sigma, not delta. If I say delta, that's just a slip up, I meant sigma f. Delta fx equals 0, but no, that's not the case. Delta fx is now equal to mass times acceleration, right? Well, what's the mass of my block? 5 kilograms. Right? What's the acceleration of my block? 2.1 meters per second, right? I don't put the units here because I'm going to get you the final answer, and that's where I'll put my units, which is 10.5 newtons. Okay? So I know the sum of the forces in the x direction are going to be 10.5 newtons, where actually, just to be safe and clarify, this is in kilograms, and this is in meters per second squared. Okay? Now, what is the sum of the forces in the x direction? Well, if I go back to my free body diagram, I see there's 2F, there's Fk, and there's going to be Fgx. Okay? So with that, I have the sum of the forces in the x direction, which are motivated by 2F, which are made up of, I'm at 2F minus Fk minus FGX. Okay, it's going to be equal to 10.5 newtons. Not 0 anymore. Well, what is Fk? I established that earlier. Fk is simply just mu k mg cosine theta. So I will take that and I will bring it down. What is Fgx? Well, Fgx is right here, mg sine theta. So I will take that and I will bring it down. Right? Minus, minus, and then 2f. And this is equal to 10.5 newtons. Well, what am I going to do? Move this expression and this expression to the other side to isolate for f, okay? So I will add both, I will add fk to the other side, and I will add fgx to the other side to remove them from this side and get them on the right side of the problem. Like so. And now I have this expression, 2f is equal to that. Well, if I divide both sides by 2, like so. Now I will get an expression that will give me the magnitude of the applied force if I am to go at 2.1 meters per second squared. And just to reiterate, this is Newton's second law. That's why I could do what I did in this step right here. Okay? So let's plug in our values. What was m given to us to be? 5 kilograms. What is g? 9.8 meters per second squared. So let's just start plugging in. So 5 kg, 9.8 meters per second squared. And then sine of theta, what was theta given to be? Well, let's check. 37 degrees. Like so. Move this a little bit to the left. So, oh, no. Move this a little bit to the left so I have more space. Plus mu k. What is mu k? Well, it's 0.24. Times 5 kilograms. Times 9.8 meters per second squared. Gravitational. That's gravity. Not gravitational constant. That's something else. That's Newton's gravitational constant is something else. And it's just gravity. Then times cosine theta. Well, what's theta? 37 degrees. And all of this, I need to add that 10.5 at the start. It's all going to just be over 2. And that's going to give me my magnitude of the applied force. So, if I'm to shove this in the calculator, 10.5 plus 5 times 9.8 sine 37 plus 5 times 9.8 times 0.24 cosine 37 over 2, and that gets my applied force to be equal to about 24.69 newtons. Hey, Mr. Wong, looking at the problem again, I noticed that they wanted f, not magnitude of f. So therefore, I would need to write direction, right? And then I would change all my absolute values to just normal f, and then I would put a plus sign at my answer. So it would be positive 24.69 newtons, taking positive to be the line of motion. That is part D. Part E. I want a free body diagram for both blocks. So I will draw a block M. And then a smaller block called big M. And then I'll be over here. Since I don't know any of the values, you cannot expect me to draw it to scale, so I will just indicate the directions of the forces. So there's going to be this tension force, which we know and establish is made up of 2F. There's going to be this FG force from the weight of the block. There's going to be a kinetic friction between here. And there's going to be a static friction between here. So I know it's going to go like this and this. And I know this kinetic friction is going to go against my line of motion. So I'm just going to draw that, Fk. And I'm going to draw Fs. I know there's going to be a normal force in response to my Fgy. think that's all the forces. Oh wait, no, because there's this big M on the little m, there's going to be a contact force that goes downwards from F of big M on little m. 1 on 2. Big M on little m. And that's my free body diagram for little m. For this one, this contact force is also going to be part of the normal force. So I'm just going to draw one Fn on top, because that's the contact force plus the reaction to the FG, y. Right, so there's my FG, there's my Fn, and then I know there's going to be static friction pulling it with this little m up here, as you can see by this. So there's going to be a Fs. There you go. And that's going to be my free body diagram, and this is my little illustration for the contact forces. Okay, so that's going to be my free body diagram. Now for part F, I wrote the values out ahead of time, so it's easier to reference to. So it wants to do when they're at the minimum applied force when they're in equilibrium, okay? So that means I know that delta Fx, so I mean sigma Fx is going to equal to 0. Because m times a, right? But if it's in equilibrium, a is 0, so m times a, so 0. Okay? I can treat this, since I know that these blocks are stationary relative to each other, as one system, because they don't fall apart, right? So I'll treat this as one whole system. Well, what's pulling the system up? 2m. But what's making it want to go down? Well, this Fk right here. And this Fgx force from the component of gravity. So there's gravity down, and then there's Fgx, Fgy is like this, and then there's Fgx like that. So that's trying to make it go down too. And that's going to be equal to 0. Right, so I isolate 2f. Add Fk and Fgx to both sides is equal to Fk plus Fgx. Okay, and now I just need to expand my equation from its variables to things I can plug in values for. So what is Fk? Well, I know it's going to be the normal force times mu k, right? Well, what is the normal force? It's going to be the weight of both these blocks, because I'm treating it as one system. I'm combining the blocks, so it's going to look like this, budget. M plus big M, right? That's going to have an Fg. And the normal force from that is going to be this Fgy right here. Okay, and this angle is the same as the angle of the ramp. I've established that. And this is going to be an Fgx right here, but this is what I worry about, Fgy. Because that, and then this is for later actually, so let's keep it here. I know Fgy is adjacent to the angle, so it's going to be mu k times Fm, right? But I established earlier that Fn is also just this Fgy, right? There's equivalent, Fgy is equal to Fn. I established that earlier in an earlier problem around here. So I'm going to take the mass, but since I'm using the whole system, it's going to be m plus m, right? Times g. And now, what component is it? Well, it's adjacent to the angle, so it's going to be cosine. Plus Fgx. Same thing, Fg. Now it's opposite to the angle, so it's going to be sine. Sine theta. Right? And that's 2f. It wants the magnitude, minimum applied force. So I'm going to do that. Divide both sides by 2. It's going to be equal to this over 2. Right? Now I plug in my values. What was mu k? 0.24. Little m was 5. Big M was 3. So I will combine those. 8 kilograms. G is 9.8 meters per second squared. Cosine. And now the angle was 37 degrees. Okay, plus another 8 kilograms. Plus m plus m. and this is 3, I mean this is 5, and that was 3 kilograms, so 5 plus 3 is 8, times 9.8 meters per second squared, right, times 9 point, nope, I already did that, times sine of theta, which is 37 degrees, right, this is all over 2, this will be delta F is equal to that, so if I plug everything in, it's going to be 2 for 4 times 8 times 9.8 times cosine of 37 plus 8 times 9.8 times sine of 37 over 2. And that's going to get my minimum applied force to keep these blocks stationary. It's going to be 31.10 newtons. 31.10 newtons. And it's going to keep these blocks stationary, and it's going to keep the system in equilibrium, so 0 acceleration. Now for part G. They want the minimum coefficient of static friction. You need to keep the top block stationary, right? Well, first off, since it's easier, let's see, what would I look at? This with Fs, but then a bunch of other stuff, or this with just simply Fs and FGY, FGX, I meant, right, on that plane? So then I will simply just look at block number 2. Well, I know that the sum forces of F and X, right, is going to be equal, well, what am I looking at? What perspective? The big M's perspective, right? So if I'm looking at big M's perspective, that's going to be big M times A. But I want to keep the system in equilibrium, right? So this is going to be equal to 0. That's it's going to be equal to 0, because A is equal to 0 at equilibrium, right? Well, in perspective, the top block, what is Fx equal to? No, it's going to be Fs and then FGX. FG's X component, right? Since my plane is going to be tilted like that, where this is X, this is Y. So it has components. So it's going to be Fs minus FGX is equal to 0, right? Well, if I add FGX to both sides, I got Fs is equal to FGX, right? Well, what is FGX? I know it's going to be this, right here, it has this FG, right? And then it's going to have 2 components. There's a FGY, and there's a FGX here, right? And this FGX, this angle is right here. This angle is also the angle of the ramp, right? Because these 2 blocks, they're going to be facing the same way. They're stacked on top of each other. So I can say the same thing about what I said for the one on the bottom, right? So FGX, it's opposite to FG, right? So it's going to be FG sine theta. Right, but what is FG equal to? Mg, big M, because that's the perspective I'm looking at. And also, I'm finding this because I know, what's it, mu s is equal to Fs over Fn. Okay, so Fs is just this, but what was sine? 37 degrees. This is equal to Fs. But what was M? And what was G? Well, G is 9.8, and M is 3 kilograms. So 3 kilograms. We expand this so I have more space. 9.8 meters per second squared. Okay. Oh, that comes out to be 3 times 9.8 times sine 37. That's 17.69, so Fs is 17.69 newtons. Right? And now I need Fn. Well, what is Fn? Let's look at big M. Big M's perspective, because that's the perspective I'm using to find Fs. Well, what is Fn? I know Fn is just going to be FG's Y's component. Right? So, if I look at that, what is FGY equal to? Well, it's going to be FG's right here, right? FGY. FGY is adjacent to FG. It's going to be FG cos theta. Well, what is FG? It's big MG. Right? But I know FGY is also Fn. right? So Fn is equal to m times g. Well, what's big M? 5 kilograms. What's little m? 9.8 meters per second squared. Ah, no, 3 kilograms. 9.8 meters per second squared. And then cosine of 37 degrees. And that comes out to be 3 times 9.8 times cosine of 37. 23.48 meters. Right? And now if I use this formula over here, mu s is fs over fn. I get my fs over fn, where my fs is this. My fn is that. Right? That gets my mu s to be 0.75. There you have it.